-1 mankilevic. That sometimes happens. Yeah. So there's also addition and subtraction with scientific notation, and you can rely mostly on your calculator to do that. But in this grade 10 textbook, they have an example which shows us how to do it. So let's quickly do that example. Our question is to add 1.99 times 10 to the power negative 26, ne? Plus 1.67 times 10 to the power negative 27 minus 2.79 times 10 to the power negative 25. And we have to work out how much that is, ne? Okay, so, oh yeah, just another thing. This is the mass of the moon. Check avocado's number. Kopela ubule a new tab molane. So that we don't, like any one of you, open a new tab and then in the search bar type Avogadro's number. I want to show you. So mass of moon is a big number. It's a positive big number. You also have smaller numbers. Numbers smaller than 0. Type Avogadro. AVO. AVO. Okay. You can see the letters now. Avogadro. AVOG. There we go. Show number 1. Avogadro's number. It's 6.022 times 10 to the. Sorry. Erin, is it 10 to the 23 or negative 23? Negative 23.
No.
Positive 23. Oh, okay. I wanted something smaller. Okay, it's fine. It's big. Let's look at this unit of measurement. Angstrom. An angstrom is a unit of length equal to 100 millionth of a centimeter. Okay. Oh man, I want something that shows how this angstrom unit in. Oh yeah, 1 angstrom is. So 1 angstrom is a unit of measurement, eh? Angstrom. It's 1 times 10 to the negative 7 millimeter. Because we measure in meters. Yeah, to the negative 10 meters. Alright. So, okay, so to the negative 10 meters means that it's 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters. So on your ruler, can you imagine this number? Because 1 millimeter is 1 over 1,000 meter, 1 millimeter. So, so 1 millimeter is 1 over 1,000 meter. This is 1 angstrom, right? Thanks, yes. Just go back to the previous slide. Slide 6, yeah. Yeah, so I wonder how you can use scientific notation. When we have a negative exponent diva so. And when we have a positive exponent, diva so. So these ones, they follow a comma if they're negative exponents, and when they don't, when the zeros are after the comma when it's a negative exponent, and they are on the left of the comma when it's a positive exponent. Anyway, so to add exponential scientific notation numbers, we must make the exponents the same. So the rules of adding exponents is that the exponents must be the same so you can add the bases. So in other words, we're going to have to use skills for maths again when adding exponents. So if we have a number x to the power b plus x to the power c, okay, maybe not. Maybe not, that's not what I want to say. What I want to share is, let's say you've got 2 to the power x equals 2 to the power 6. Do you know what the solution for this is? Oh yeah, thanks. 2 to the power x plus 2 to the power 6 simply tells us for x equals 6, ne? And that's because the bases are the same, therefore we can equate the exponents. We have to use a similar kind of thinking, ne, to add these scientific notation numbers. And what we do, we can choose whether we want to work with exponentia minus 26, exponentia minus 27, or exponentia minus 25, ne? And we must make them all the same. So if we look at exponentia minus 25, then we will have 1.99 times 10 to the power negative 26. We say 1.99 times 10 to the power negative 26, and then we divide it by 10. So I divide by 10, we will have 0.199 times 10 to the negative 25. Now effectively what happens is that we have 1.99 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, ne? When we divide by 10, we simply shift the comma that side, and then it becomes 0.199 times 10 to the negative 26. So when the comma shifts to the left, the marking. Okay, let me think of a better way to explain this. Let me think of a better way to explain this. Because maybe these numbers are a bit too big. Let's start with something small. Ne? If we have 10, it's the same as 1 times 10 to the power 1. Ne? If we have 100, it's the same as 1 times 10 to the power 2. If we have 0.1, it's the same as 1 times 10 to the power negative 1. If we have 0.01, it's the same as 1 times 10 to the power negative 2, because this 2, the comma shifted once, twice, in that direction. When we have 0.001, that is the same as 10 to the negative 3. Why? It tells us that the comma shifted 1, 2, 3 times. 1, 2, 3 in that direction. So if you have 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 199. Ne? This is what equals 1.99 times 10 to the negative 26. Because we've got 26 zeros all the way to there. 26 zeros. All up. All up. That's fine. Okay. So we've got quite a number of zeros there. Now, in order for us to make it a layer 25, we want to shift the comma this way, right? We want to shift our comma once to the right. So meaning more shift but or how else can I explain this so that the scala will do? Okay. Oh, okay. Remember when you have a number, x to the power a times x to the power b, then it's the same as x to the power a plus b. And also when you have x to the power a divide by x to the power b, it's the same as x to the power a minus b. So let's keep this in mind. Right, so in order for us to make this times 10 to the negative 25, it means the exponent will have to have plus 1 added to it. So when we have plus 1 added to it, there will be minus 26 plus 1, which gives you minus 25. Let me just blow my nose. Oof. Okay, so it will be minus 26 plus 1. So to equate the exponent here minus 26 to here minus 25, we'll have to multiply by 10 to the power 1. Because when we multiply by 10 to the power 1, it reduces the number of zeros here to 25. Multiplication or division tells us how many times the multiplication or division by multiples of 10. How many times our comma shifts from 0 comma going in that direction. So in other words, to go from exponent negative 26 to exponent negative 25, we'll have to multiply by 10. So to go from exponent negative 27 to go to exponent negative 25, we'll have to multiply by exponent 10 to power 10 to exponent 2. So what this means is 1.99. So 1.99 times 10 to the negative 26. We multiply it by 10. And then the 1.67 times 10 to the negative 26. We multiply 100, and then we take 2.79 times 10 to negative 25. So what we're going to have is we're going to have 0.199 times 10 to negative 25 plus 0.0167 times 10 to negative 25 minus 2.79 times 10 to the power negative 25, and re-add then. So because the exponents are the same, we can simply add the 2.79, negative 2.79, to 0.0167 and 0.199, and the answer then becomes negative 2.5743 times 10 to the power negative 25. Let's do a different example. We want to add now that we follow the same process. Okay, let's do this one. 5 times 10 to the power 3 plus 4.2 times 10 to the power 4. Yes, you can change there. 4.2 times 10 to the power 4. So we want to make sure that these exponents are the same. So we can multiply. Again, in the other one we multiplied so that we can add the exponents. So we can multiply the smaller exponent, 3, by 10, so that really no, wait, it's gonna be, it's gonna be multiplied by 10 anyway, so it's gonna be 5, or rather let's say 50, yes, 50 times 10 to the power 4 plus 4.2 times 10 to the power 4. No, wait. 5.1 there. 5.1 times 10 to the power 3. It's the same as 5.1, 1, 2, 3. Okay, I see what's going on. We can have, this one is 5,100 plus 42,000, and this is 47,100. Yes, and this is the same as 4.71 times 10 to the power 4. So so there's two ways to with these ones study negative exponent, you can just multiply, you can just pursue to make them the same as the smallest exponent. And how you do that, it's either you multiply by 10 or factors of 10, so 10, 100,000, to get to there, because the goal is to have the exponents subtract each other to the point where they're equal to the smallest exponent. And then Moki Keropile, but I want to explain it the same as the other one. So we can apply the opposite and have 42 times 10 to the power 3 plus 5.1 times 10 to the power 3. And then this becomes 47.1 times 10 to the power 3. And you can also divide by 10 so that it's 4.71 times 10 to the power 3 if you divide by 10 here. Or you can also say 5.1 times 10 to the power 3 is the same as 0.51 times 10 to the power 4, meaning you divide it by 10, and that means 5.1 times 10 to the power 3 plus 4.2 times 10 to the power 4 is 0.51 times 10 to the power 4 plus 4.2 times 10 to the power 4, and that's 4.71 times 10 to the 4. So that's how you think about them. So to add the negative exponent, you can simply multiply by 10 to the 1 or 10 to the n, depending on how many zeros you need to go down by. So 25, we need to go by 1 0. For 26 to go to 25, and for 27 to go to 25, we need to go by 2 zeros. So our like multiply 10 to the negative 2, 10 to the 2, 10 to the 1. And that gives us the 25s. Yeah. And then to add positive ones, you can still apply the same principle. So we divide like 10 to get 4.71 times 10 to the 3. Yeah. This is supposed to be a 4 here. Yes. Okay, scientific notation. I don't think you guys get it now, but can we say I understand? That's fine. So we don't spend too much time on it. There's also multiplication and division with scientific notation. And this one does not need to be the same. So for multiplication, we add the exponents and multiply the n terms. So I agree. For scientific notation, we have the number times we have the number times 10 to an exponent, right? So we multiply the n terms and we add the exponents. Okay? And how we see that? If we near 1.6 times 10 to the negative 19 multiplied by 3.2 times 10 to the negative 19 divide by 5 times 10 to the 21 times 10 to the negative 21. We can simply have 1.6 times 3.2 times, or divide by 5, ne? Then it over times 10 to the power negative 19 minus 19 minus negative 21. Do you understand why I put in minus negative 19 minus negative 21? That's because if we're adding the exponents here, it's that one plus that one minus this one, because the multiply tells me that I'm going to add the exponents, the divide tells me that I'm going to subtract the exponents. So we can make it simpler by starting off first with JHD multiply. So it's going to be 1.6 times 3.2, 1.6 by 3.2 is going to give us 5.12 times 10 to the negative 38. And then that's this part, ne? This is 5.12 times 10 to the negative 38. And then to do the whole problem, it's going to be this divided by that. So it's going to be 5.12 times 10 to the negative 38 divided by 5 times 10 to the negative 21. So because of the divide, I subtract the exponents. 5.12 divided by 5 times 10 to the power negative 38 minus negative 21. And then this equals, what's this? Divide by 5. 1,024 times 10 to the, what's 38 minus 21? It's 17. Yeah? Oh, it's 18. Negative partial guy. Okay. My cloth is so dirty. Sorry. Okay. I just want to see you now. If I textbook. 5.12 10 to the negative 38. So 2.56. Wait, now where does this 2.56 come from? Okay, that's not correct. 5.12 divided by 5. 19 years or Rama, because the exponent we started with was 19, 9 clean, and then the other one was 21. But anyways, I think this is a typo, guy, because if we follow the math correctly, 1.6 times 1 times 3.2 is 5.12, right? If we're gonna add the exponents, negative 19 plus negative 19, we get negative 38. So this is fine. The second part, this 2.56, I'm not sure where it comes from. It's just supposed to be 5.12 to the 38, to the negative 38. Divide by 5 times 10 to the negative 21. So Raraki, 5.12 divided by 5 times 10 to the negative 38 minus, because of that divide, and negative 21. So that makes it 38 plus 21, which is negative 38 plus 21, which would be positive 70. Yeah. So I think more than a typo. But the same math we can use for positive numbers as well, where we have to add exponents and the things are positive. Ugh, gross. Okay. Yes. So there's different types of units. SI units. SI stands for Système International de Unités, which means International System of Units. My French is not that great, so you can pardon it. But yes, but the long and short of it, we have basic units that we use, SI unit system international. The other type of unit systems ke imperial. That's used in I think Britain and I think in the United States and other countries, right? And then there's natural units, which are the most sophisticated. The argument for this choice is that all the other quantities should be built from these fundamental units. This system is used in high energy physics and quantum mechanics. So, right, so natural units, an example of this is the measurement of the second. The second that we use in time, it's actually calculated using, is it CERN, that laboratory that makes it? How do they define the measurement of a second? And then from that second, we can define any other quantity. But units are important. Length, mass, time. What unit do we use for length? You wanna guess? Time, temperature. You can guess. You cannot be yeah. So for length, what units do we use? Meter. And then for mass, kilograms. Where shashumishi the word weight? Do you wanna guess? Mass versus weight. Why don't we use the word weight? Weight again? Okay, the basic reason why weight is because mass is how heavy an object is, but weight is actually a force. And the definition of a force from Newton is that it is the mass of an object times a form of acceleration, right? And that acceleration, do you want to guess what that acceleration is that gives any object of a mass a weight? The acceleration, do you want to guess what it is? Mike, did it? How is it? The acceleration that gives an object weight. So that weight is a force. You're not sure? Okay. So, how force something into the air? What happens to it? It will fast. Okay. Why?
Because of force of gravity.
Okay. So, that force of gravity, the correct way to use that terminology is that the object in a mass, and because of its mass, when it's in the air, it drops down because it accelerates. Why does it accelerate? Because there is a force of gravity that the object is pulled by to the center of the earth. And that acceleration is the acceleration due to gravity, which is 9.81 meters per second square. Right. So yeah, weight and mass are not the same thing, because weight is a force where the object's mass times the acceleration due to gravity accounts for that force. Combinations of SI units. So from these units, we can get other units. For example, if we calculate momentum, momentum is mass times velocity, which is kilograms times meters per second. And then it gives you momentum as units of kilogram meters per second. Force is mass times acceleration. Mass kilograms the units, and acceleration is meters per second squared. So any force is calculated, is measured in kilogram per second squared, but simply Newton, after Sir Isaac Newton, who contributed a lot to our current understanding of the mechanics today. Yeah. Prefixes of base units. Oh, okay. So whenever you have units, at certain multiples they start having prefixes. So after 1,000 meters, you have a kilometer. You get it? After 1,000 grams, you have a kilogram. After 60 seconds, you have a minute. But that just goes to show how the naming of the units change when you get to a certain threshold, a certain limit. After limiting it, then the things change. And then back to the same units. So wo kilogram it's 10 to the 3 as scientific notation. Salwa kwa ba bolela ka ditaba tša Eskom, load shedding and stuff. They always use so many megawatts, so many gigawatts. Azanko kwa ba bolela ditabeng that thing. That's it. Must listen to those things, especially ba bolela ka Eskom, because they speak about units we use in electricity, power, watts, kilowatt hours, etc. So what do you, for example, the units kilowatt hours, kilowatt hours. So in other words, it's 1,000 watts per every hour used. Eskom and a supplier in the millions and billions of watts. Like watt is a unit of power. Your calculator has a certain amount of watts. You can check. It's 0.0002 watt. So shear, that's the power rating. Laptop in your cell phone in but that's just how you measure the power. And then electricity generation is measured in mega or gigawatts. So example, 40,000 meters can be 40 kilometers. 0.001 gram is the same as 10 to the negative 3 of a gram, and it's 1 milligram. 2.5 times 10 to the 6 Newton can be 2.5 meganewton, which is like if you're going to work out how like the forces and the stress and the stresses like a building. It can be a dam, it can be a high-rise building. If you want to work out how heavy that forces of the building is on the area that it covers and the pressure that it applies, your forces are usually in meganewtons, because then over the area, the stresses or the pressure becomes megapascals. And there's other units that you can do that with. So do you have this learning guide? Because I think you're really on Classroom. I want to share this homework so that you do these exercises. This exercise 1.1. Most likely how I ask for my homeworks to be submitted. Yes, so yeah, okay, it's interesting. So I want us to do page 8. Page 8 of Siyavula Learning Guide, Siyavula Grade 10 Learning Guide, Dear exercise 1.1. Magdalene, you'll have to excuse my slow pace today, we're gonna go pick up the pace. But I really want to make sure these basic concepts you understand, because what happens is when you get to matric, you don't want to be wondering now what are the basics. And Musalwena, I want you to say, oh, this is how it connects to what I'm going to write about. And this is how it starts when it's item around it. So I want you to do exercise 1.1, all those exercises 1, 2, and 3. Lerato Tema, I will have to add you onto the grade 12 class for now. No, not localhost, I want classroom. Yes. Ladies, I think we can stop here for today. And then, yeah, let me add. We can stop here for today, ne? Joy is in, okay. Then, okay. So just go through there. There's some learning guides. Learning guides, it's like grade 10 to 12, they're all in here. Ne? Now when I put in things, I'll just add them here. That's for grade 10, for grade 12, sorry. But for you, grade 12 physical science, grade 12, I wanna see class announcements. Mind the gap. Where did I put those things? Learning guide, she. Yes, yeah, okay. I guess. Okay, great. Let me add you here. Alright, cool. I'll add you there. And I think grade 10. Yeah, so you've got physical science and maths study guide, ne? So I'll just get that on the air there. Just add you. TH. Yes, there we go. Alright, so yeah, for today, just pausing our slowish pace. Kawana Nagunji, we'll pick up the pace. Yes, I just want to see, could you get rid of guy? Material. Oh, no, not this one. Grade 12 science. Guy. Oh, okay. Huh. I haven't really used this much, eh? Can use it more and more and more. Okay. Yeah, so ladies, let's stop here for today, and then next week we'll start from these basics. What's this? Scientific skills for science, and then we'll carry on from there. Really conversions, né? So in other words, converting from one unit to another. And then we'll also do rate, proportion, ratios, etc. Right, so proportion, ratios, level rate, they're important because, like I